Hey everybody, I want to talk about measures of spread or dispersion in this video. So let me share up a screen here, and then we'll talk about why we want to do something like that. Ooh, where's my, oh yeah, it's the whiteboard, sorry. So we're going to talk about three measures of spread. I'm going to go from the simplest to the most complicated. And talk about the relative values of each one. So the easiest measure of spread. So I'm gonna make a for here. I want to make some data. So here I've got a couple of scales. Let's say I have some data that's like here and here and here, here. All right, so I've got some reasonably spaced data. Cluster up a little bit over there. Okay, so the range is just the difference between the maximum value and the minimum value. That's it. It's literally max minus min. That and then whatever that number is the range. Now that works okay. It's not the best or worst of the measures of spread, but it's a little coarse. Like you can imagine that it's pretty easy to get a range that doesn't do a very good job of representing your data. Now, in this case, it's probably fine, right? So the range goes from here to here. It's whatever the length of that line is. I didn't put a scale on this, so you can't really tell. But if you compare some relatively evenly spaced data like that to some data that looks more like this, so there, here, here, we've got a bunch of data all clustered over here, and then one over here. You might notice that the range there is the same, right? And it does not do a good job of distinguishing between data sets that look like the top one and the data sets that look like the bottom one, right? The range, so like other one number metrics for saying how spread out a data set is, range is pretty problematic, but it's more problematic than most. And this is why. Range only cares about the minimum and maximum value and tells you nothing about what happened in the middle, right? Which is where most of your data is. So we don't typically use range. It's not the worst thing if you want like a quick and dirty representation of how spread out a data set is, but I generally would not use it because it ignores the important part, which is the middle, which is kind of bad, and you don't usually want to do that. So what are some other ones? Well, to describe the next one to you, I first need to describe what quartiles are. And I'm realizing now that my R looks exactly like a V. And let's make that not the case. Let's make that an R. R. There we go. That's a sloppy R, but good enough. So quartiles are dividing lines in your data that divided into 4 equal pieces. So if I visualize my data set as this line, then your quartiles are going to be the numbers that divided into 4 equal pieces. So this is quartile 1, which we abbreviate Q1. This is quartile 2, which we abbreviate not Q2, but I'll put it like that for right now. And then this one is quartile 3, which is apparently bigger than the others and is abbreviated Q3. We don't usually call the middle quartile, quartile 2. We typically call it the median. That's what the median is. It's the dividing line between the top half and bottom half of your data. And that's what all the quartiles are. They're the dividing lines between the bottom quarter and the second quarter, and the second quarter and third quarter, and third quarter and fourth quarter. That's all quartiles are. There are plenty of others of these, by the way. You've probably heard of percentiles, I would imagine, which doesn't divide your data into 4 equal pieces, but instead divides it into 100 equal pieces, each one of them being 1% of the data. There's also deciles and quintiles that divide it into 10 pieces and into 5 pieces. I'm not going to worry about those. We're never going to use those. We'll talk about percentiles, but I won't calculate them. Quartiles, though, we're going to use a fair amount for the following reason. Well, let me describe them a little more, and then we'll talk about the reason. So we're going to use quartiles a little bit more often than the other two. And the way you want to calculate quartiles, well, okay, the way you really want to calculate quartiles is you want to have your calculator do it, or you want to have a computer do it. But if you're doing it by hand, the basic way to calculate quartiles is to calculate the median first, right? Remember the n+1/2 formula from the last video. Calculate the median first, and then use the bottom half of your data, using just the bottom half of your data, calculate the median of that, and that'll give you Q1. And using just the top half of your data, calculate the median of that, and that'll give you Q3. Right, so you basically just calculate the median 3 times, but you don't use the whole data set. You only use the bottom half of the data set for Q1, and the top half of the data set for Q3. But the way you really want to think about quartiles is that they're the dividing lines that divide your data into 4 equal-sized chunks. Now, the reason I bring this up is the next measure of center that we have is the interquartile range. So the interquartile range, or IQR for short, because I don't want to write out interquartile range all the time, is the difference between Q3 and Q1. Which is, given the name, kind of exactly what you'd expect, right? Range was just max minus min. So range means how far apart something is, how far apart 2 things are. Well, the interquartile range is how far apart your first and third quartiles are. So that's why it's called that. This is a better measure of how spread out data is than just the range, because the first quartile and the third quartile, which by the way, I should mention are the 25th percentile and the 75th percentile. I don't know if that's obvious or not. This is the 25th percentile. And this is the 75th percentile. And what I mean by that is that the 25th percentile is the value that has 25% of the data below it and 75% above. And the 75th percentile is the data value that has 75% of the data below it and 25 above. So if you take a standardized test and you score in the 80th percentile, that means that you outscored 80% of people and were outscored by 20% of them. So that's the connection between percentiles and quartiles here. But anyway, the first quartile means that a quarter of your data is below you and 3/4 of the data is above. And third quartile means the opposite, right? 3/4 of the data is below and 1/4 is above. So the interquartile range is just Q3 minus Q1. It's literally just that value. It's the range between the first and third quartiles. This is sometimes used. If you read your book and it talks about how to calculate outliers, they're going to use IQR for that. And I don't know why. It seems like a very strange way to do it because we don't really use quartiles for much else. Now we do use them for box plots, which I'll discuss in an upcoming video. But for now, I just want you to know what the interquartile range is. It's just Q3 minus Q1 in the same way that range is max minus min. Both pretty rough-ish descriptions of how spread out data is because they ignore big chunks of it, basically. So let me have another data set here. So say I've got some data. Go back to my my large red data values. So let's say I have some data here. And it looks like this. So the first and third quartiles are like they're medians basically. So when I say divides the data into 4 equal pieces, how many do I have? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have 15 data values here. So the median is going to be, let's see, let's do this in blue. The median is going to be 15 plus 1/2, which is 8. That's the 8th positions. 1, 2, 3, 4, 5, 6, 7, 8. So this one right here, this dot right here, we can see this. is the median. Forget that one that I've outlined in blue. That's the median. So the first and third quartiles are going to be I'm going to use the bottom half here and then the top half here and find what positions those are in. So there's 7 in the bottom half and 7 in the top half, plus the one in the middle is 15. So of the 7 in the bottom half, I'm going to do 7 plus 1 over 2 is 4. And I'm going to look in the 4th position, 1, 2, 3, 4. So this right here, that's my Q1. And then 1, 2, 3, 4, this one right here is my Q3. It's not a very good Q, but just roll with it. I promise this is a Q right here. Q, there we go, Q3. And so the interquartile range in this case is just how far apart these things are. That's the IQR. Now, unlike the just range, this doesn't ignore the middle portion of the data. It sort of highlights it, right? This is the middle 50% of the data. I hope that's clear that that 50% of the data is between Q1 and Q3, because 25% is below Q1 and 25% is above Q3, leaving you 50% in the middle. So that means that half of my data is between Q1 and Q3, and that's what the interquartile range tells you about, right? It tells you how far apart the edges of the middle 50% are. The problem with IQR is that it ignores everything else, right? So it ignores it ignores all this stuff, and it ignores all this stuff. And those things are not relevant at all to IQR. So in the same way that range only concerned itself with the most extreme values, the minimum and maximum, interquartile range only concerns itself with the middle 50% and ignores the minimum and maximum. So yeah, also problematic, probably a little bit less so because it's really dealing with the typical values, the middle 50%, which is kind of typical ones. But still not the greatest in my opinion. The gold standard of measures of spread is standard deviation or variance if you are a statistician. And by that, I don't mean that those are the same thing. I mean that statisticians tend to use variance and most of the rest of the people tend to use standard deviation. And I will explain why in just a second. So standard deviation and variance are totally different than range. So here, I'm gonna explain what standard deviation is roughly. And then I'll show you the formulas for it and show you why I said roughly. So let's say I have some data values here. I don't want to use too many here because I want to draw a lot on this. So the way you want to think of standard deviation is that standard deviation is the average distance from the mean. So what we're going to do is, first thing we're going to have to do is calculate the mean of this, which I am not going to do precisely. I'm just going to estimate it, right? So I would say the mean of this is probably about here, maybe. Yeah, something like that. Close enough. Mean. And then what we're going to do is we're going to measure how far away each value is from that. So for instance, this first value here, we're going to see how far that is right there. And then for the second value, we're going to see how far that is. And then we're going to see how far this third value is. And I'm not going to write in all the bars. You get the idea, right? We're checking to see how far away each thing is from the mean. And then we're going to average all those distances. And that's roughly what standard deviation is. I'm lying a little bit. I'll show you in a second. But that's basically what standard deviation is. It's an average distance away from the mean. So instead of measuring how far apart values in the data set are from each other, we define a central value and find out the average distance from that. And that's standard deviation. Given all that, the way you really want to think of standard deviation is bigger means more spread out, and smaller means less spread out. And that's it. That's really the way you want to think of it. It's a little bit more nuanced than that, but remembering that is basically what you want to do. Like that's the basic rule of thumb. Bigger standard deviation means more spread out. Smaller standard deviation means less spread out. Same thing with variance, by the way. Variance is just standard deviation squared, where bigger variance means more spread out, smaller variance means less spread out. That's the way you want to think of it. Now, standard deviation and variance certainly have their own problems. For instance, if you get a very non-standard looking data set like this, where we have something highly skewed, where we have most of our data is clumped up in one region over here, let's say, and it's not very spread out at all, and then there is one or just a couple of outliers. Remembering that outliers are things that are far away from the rest of the data values. What you're going to find is that, so my mean is going to be over here somewhere, right? My mean is like there. And so the average distance from the mean is going to be pretty big in this case, because everything that's small is pretty far away from the mean, and the outliers are also pretty far from the mean. So what you end up with is this relatively large standard deviation for a data set that isn't really all that spread out, right? It's almost all your data is right here with an outlier, one single outlier over here. So arguing that your data set is very spread out is, I think you're on shaky ground there, right? The data set's not really all that spread out. It's clustered together plus one giant outlier. And the standard deviation in this case is actually quite big. It's going to be pretty large. And that's just something you have to live with when you're trying to use these single number metrics, right? If I'm trying to describe how spread out a set of data is, and I'm trying to do that in one number, it's never going to capture all the nuance. It's just not. Standard deviation is generally considered pretty much the gold standard for how spread out, or for measuring how spread out things are. IQR with its ignoring the extremes, and range where it's ignoring the middle. Those things are not great. Like they're too not great, basically. To use, and so we use standard deviation, or as you'll see in a little bit, variance. Variance is literally just standard deviation squared. So remember I said that standard deviation isn't exactly the average distance from the mean. It's not. So let me show you how they're actually calculated. The formulas are going to look complicated, and they kind of are. And I'm going to talk through what they mean, and then we're going to do it in calculator and on Google Sheets, because those things are easy. There's a command for them. So the formulas look like this. And I just used the symbols here instead of labeling them. So these guys are variance. And you might notice that I have two formulas for each one. And this is standard deviation. So here's what the formulas are. So let me talk about this one first. So a couple things. Number one, the symbol for population mean is this fancy looking U, which is actually a Greek M, called a mu. So the symbol for population mean is this number, or is this symbol right here. The symbol for sample mean is this, X with a bar over it. That's the one the calculator uses. The reason for these two different symbols that both mean average is that, well, let me direct your attention back to topic number one, which was terminology. And I talked about the difference between parameters and statistics, right? So mu is a parameter. That is the average value of everything in the population. It's unchanging, it's fixed. And it's usually a thing that we're trying to estimate and don't actually know. X bar is the symbol for sample mean. this number is a statistic and it changes depending on what members are in our sample. That's why we have two different symbols for it. One's a parameter, one's a statistic. And I know that distinction still seems, no matter how much I say it, it's not going to really stick with you how important it is until we start doing actual testing, at which point it will become very obvious why it's important. But that's the reason for having two different symbols. So here's what we're doing to calculate the standard deviation of a sample. And I'll explain why there's different formulas in just a second. So X, these are data values. X bar is the sample mean. So X minus X bar is how far away a data value is from the sample mean. So something like, oops, I went too far, something like this. Right, so this number X, so this is an X right here. One of these dots is X. So X minus X bar in this case, so the mean is right here, X minus X bar is negative because this number is smaller than this number. So when I subtract, I get a negative number. When I do X minus X bar for this number right here, I would get a positive number because this number is bigger than the mean. So we calculate all those things, X minus X bar for everything, then we square all of them, divide by n minus 1, so 1 less than the sample size, which we'll talk about in a second why you'd want to do that, and then take the square root. So this X minus X bar, we call that a deviation. So this is the average of the deviations, almost. It's actually the square root of the average squared deviation, which sounds like it would be, you're taking the square root of something that's squared, they just cancel. But no, because we're not just doing that. We're adding them all up. That's what this says. So this is really X minus X bar plus the next X minus X bar plus the next X minus X bar, squaring each one and then taking the square root of that. And if you remember your algebra, that does not, you can't do that. Those don't cancel. Like this squared and this square root don't cancel. Now, and a completely untruthful answer or reason for why we would square these and then add them all up and then take the square root is that we want to make them positive, right? So it turns out that if you just do X minus X bar without squaring it and add those all up, the thing you get is always 0. So if you just add up all the deviations from the mean, some of which are negative and some of which are positive, it will always come out to be 0, which is obviously that's not useful. If we're just always getting 0. So an untruthful reason for why we do that or why we square this is to make them all positive, right? You square something negative and it becomes positive. Then we average them, although not quite averaging, right? We're not dividing by n here, we're dividing by n minus 1 for a reason that I'll explain in a second. And then we take the square root of that. So that's what we're doing with the formula. So let me explain what we're actually doing, why we add up all these things and then square them and then divide by n minus 1 and then take the square root. So data values, how can I say this? The answer is honestly too complicated to explain in this class. I really would need you to have taken some linear algebra to understand the full explanation here. But I'm going to make an analogy that is actually true. Like this analogy really is the reason that we do this, which is Pythagorean theorem. So it turns out that you can think of data as points. Vectors, actually, if you're familiar with the term, but points are fine. And so if I have two data values, this one right here and this one right here, and I'm trying to find the distance between them, which remember, that's what standard deviation is. It's average distance between data values and the mean, but you can think of it as average distance between data values as well. Again, it's an analogy. The way you would find these things is with Pythagorean theorem. The way you'd find the distance between these is with Pythagorean theorem. You would find out their x distances away. So this is what do I say here? Delta x. So how far apart they are in the x direction. And then you would find out how far apart they are in the y direction. Delta, by the way, is the usual accepted symbol for how far apart things are. Right, so this delta x is how far apart they are in x direction, and the delta y is how far apart they are in the y direction. And what you would do to find how far apart the 2 points are diagonally is you would do delta x squared plus delta y squared. And then you take the square root. Right, and this process of adding things up and squaring things and then adding up those results and then taking the square root is actually how we find distances in 2 dimensions. Now, it turns out that's actually how we find distances in 3 dimensions or 4 dimensions or more as well. You just have delta x, delta y, delta z, delta w, delta t, and you do exactly the same thing of squaring and square rooting, or squaring, adding up, and square rooting. And it turns out that that is actually the proper way to think of data points, is in multi-dimensional, what are called vector spaces. And so that's what we're doing here. This sum of squared deviations is actually the right way to think of average distance, believe it or not. And so this reason right here, this complicated reason of why we might do that is the real one. This is actually why we're doing that, as opposed to just trying to make them all positive, right? If we wanted to make them all positive, we could just take the absolute value and do that and average those. And you can do that, by the way. That is another measure of spread, but it's not this one. So let me bring up one more point, which is why we divide by n minus 1 as opposed to n. By the way, capital N is population size, lowercase n is sample size. So why do we divide by n minus 1 rather than just n, right? If I'm trying to find the average distance, shouldn't I be dividing by the number of things in my data set? And the answer is not in this case, no. And I will explain more when we get to t distributions and start talking about degrees of freedom a little bit. But essentially, the way you want to think of S, so S is the symbol for sample standard deviation, and sigma is the symbol for population standard deviation. The way you want to think of S is that it is estimating sigma, right? That's what our statistics typically do, is we're going to use our statistics as proxies for parameters. The parameter is the thing we really want, but we can't get it because there's no way we can sample the whole population. So instead, we use a proxy for it. In this case, the sample standard deviation. And it turns out, via math that is way too complicated for this class, that we can show that S typically underestimates sigma by a factor of n over n minus 1. And so instead, we can do some semi-fancy algebra and show that then that means that you should divide by n minus 1 instead of n, but that is what it means. The reason we're dividing by a smaller number instead of the actual n is that this number underestimates the number that we want it to be approximating by a factor of, like I said, n over n minus 1. N minus 1 over n? No, by a factor of n over n minus 1. That's how much it underestimates it by. And so we divide by n minus 1 rather than n. Yeah, all that said, let me reassure you that I will never ask you to calculate standard deviation or variance by hand. Calculating this stuff by hand is nonsense. There's absolutely no reason to do it, in my opinion. We're just going to use the calculator and computer. I really just wanted to show you the formulas so you could so you could see sort of what my description looked like in formula form, right? Average deviation from the mean kind of looks like this. This is actually, average, scale, the square root of the scaled squared deviations from the mean, but thinking of it as average deviation from the mean is a lot easier to think about and basically correct. Like, I know I've been talking about how this formula doesn't actually match up to reality. You can't really like square root a bunch of stuff that you've added up. But thinking of it as average distance from the mean actually works out quite nicely. So that really is the way you want to think of it, even though the formula doesn't really look like that. Okay. So that said, this is the formula for standard deviation. You don't have to remember that. I'll never ask you. I'll never ask you to use it. You can just do it all in your calculator and or computer. I certainly would never want to calculate standard deviation by hand, and I'm not going to make you. Doesn't seem to serve any purpose to me. Now, the one thing I do want to mention is variance. We're going to use variance a little bit later. The reason we don't use variance, but statisticians do. So firstly, let me just point out, variance is literally just square root with is just a standard deviation with the square root off it. That's all it is. Literally just drop the square root and you get variance. So the reason statisticians like variance is that variance has much nicer properties than standard deviation does, much nicer calculation properties. So if you want to, for instance, add two standard deviations together, the thing that you will get is not another standard deviation. It doesn't work like that because of the square root schmutzing everything up, right? It's just getting in the way of all the math that we might want to do with it. And variance doesn't have that problem. Variance has nicer mathematical properties where, like, you can add two variances together and get another variance. And we will actually do that when we get to two sample testing. I'll explain how we're going to use that then. On the other hand, the generally accepted interpretation of standard deviation as the average distance from the mean variance doesn't have that. Variance, the units on variance are weird. Like, for instance, let's say we wanted to find the standard deviation of incomes in the United States, which I think I still have that up here somewhere. Not that one. This one? It's not that. It's this. Right. So here's my graph of this is incomes in 2014 in the United States. I could find the standard deviation of this data set. And the standard deviation would be the average distance from the mean. And if you remember, the mean was 72,000 and something dollars. And so I could say that the average distance from that is in dollars, because distance in X terms here is number of dollars, right? That's what my x-axis is dollars. The variance would be that number squared, but the units are dollars squared. And what does it even mean to have dollars squared, right? And so that interpretation is weird. And it's why we usually use standard deviation when we're teaching about measures of spread as opposed to variance, which is slightly easier to calculate, has nicer mathematical properties, and has a crazy interpretation a lot of the time. It's very, very strange. You can get much weirder ones where you have, like, it's not even something squared. It ends up being like something to the 3/2 or whatever, it's a mess. So good interpretation, bad calculation. Bad interpretation, good calculation, essentially. And the one we're going to use most of the time is standard deviation, which I'll explain why when we get to central limit theorem and all that, where it becomes a lot more important for us. Yeah. But that's all variance is. Variance is literally just standard deviation with the lid off of it, essentially. Okay, so I've introduced a bunch of symbols. Let me give you this little chart here. So you might want to write this down. I've got population and sample. And so these things are parameters and these things are statistics. And I'm just going to put the symbols in here. So the population mean symbol is mu. It is a Greek M. It looks like a U with two tails on it, which kind of is, to be honest, but it is a Greek M. The symbol for sample mean is X with a bar over it. pronounced X bar. Symbol for population standard deviation is a sigma, which is a Greek S, a Greek lowercase s, actually. Looks like an O with a tail on the upper right. Oh, excuse me. The symbol for sample standard deviation is S. Now, you might notice a running theme here that parameters tend to be Greek and statistics tend to be American letters, English letters. I guess those are Arabic symbols. I don't know. Standard, I'll say American. I know they're not, I know they didn't come from America, but I'll say American. Or English, I guess. And then we go ahead and break that tradition right off the bat. So the population size is capital N. I don't know why it's not a nu, which is the Greek N, but it's not. And then sample size for samples is lowercase n. That trend that I mentioned about parameters generally being Greek and statistics generally being English letters mostly holds. We will break that tradition a few times and use it a few times, but thinking of it as a general rule is probably pretty good. Like that'll work out fine for you. Okay, so let me sum up this video that has been, I think, exceptionally long. This has got to be closing on an hour at this point. If we're trying to describe how spread out a data set is, we basically have three main options: range, IQR, and standard deviation or variance. Range and IQR both have their own problems of ignoring big chunks of the data. So range ignores everything but the max and min. IQR ignores the min and max and only pays attention to the middle 50%. And those are basically too problematic, and we don't use them most of the time. We use almost always standard deviation or variance, which for us is mostly going to be standard deviation, at least at the beginning of this course. And standard deviation is the average distance from the mean. It's not really, but that's how you want to think of it. Standard deviation is average distance from the mean of everything in the data set. So by the way, I should point out, you can't have standard deviation of a point. That doesn't make any sense. Standard deviation is a property of an entire set of data of which you calculate the mean and then find the distance to each thing in the data set and then average those to get the standard deviation. And again, I know I'm lying on the formulas, but that is a good way to think of it. And then variance is that number, but squared. And then we've got the different symbols for them. For means, we've got mu and x bar. Standard deviations, we've got sigma and s. Samples or size, we've got capital N, little n for population and sample. And you're going to want to remember these. We're going to use these all semester long. Make sure you know them. Okay, so the pluses and minuses of each are just what sort of data set you want to be deceived by, essentially, or not even that. It's really the way in which outliers are going to screw up your metric. Here, outliers, by having a large distance away, screw up your metric by making it much too big. Here, outliers screw up your metric by the fact that IQR ignores them entirely and doesn't account for them in any way. So totally the opposite of range. And then standard deviation and variance, they get skewed by outliers, but not quite as much as, say, range, for instance. And so we generally end up using this. And again, trying to use one number to describe how spread out your data is going to be fraught with problems because data just doesn't necessarily all look the same, right? It's not all nice like this, where standard deviation and variance give you a great measure. Sometimes it looks like this and is messy. And we'll talk more about outliers in our outlier video, which is coming up next. Or I guess I don't remember what order I'm going to put them in on the website, but it's one of these videos. Okay, so let's go see how to do this on calculator and computer. I'm just going to show you how to do it in Sheets. I believe I can't use this data. I have to use something like this. Yeah, So this is the same data I had from my mean and median video. So if I wanted to find the standard deviation, I would use the command st.dev, I think. Is it st equals st? Yeah. So standard deviation right there. P and S, standard deviation of a population, standard deviation of a sample, right? So you might notice that stand_dev.s, they just call that standard deviation. That's the same thing as this, whereas this is standard deviation of an entire population. The reason they're using the sample formula, just as the default, is that if you have the data for it, that's almost certainly your sample, right? It's very rare that you will actually have the entire data for population. So in general, that's the one we use. We're going to use the sample one. Now, again, I want to find the standard deviation of all of this stuff. So I'm just going to pick, so you can see here, this really just says put in a bunch of values here, right? So standard deviation of 1 and 2, it would calculate, it would have this as my data set. I want to do all 500 things, all 500 things in column A. So that's what I will put in. It'll take a second to chug out a standard deviation. So 4.36 is my standard deviation. Now I should point out that you can also calculate the quartiles. So Q1, Q3. So if I wanted to calculate, I hate that it recalculates the same every time, I'm sorry, but the formula for Q1 and Q3 is equals quartile, I think, right? Yeah, it's quartile. Quartile, and you have to tell it which data, then comma, which quartile you want. So I want this as my data, comma, the first quartile. And there it is. And I can do the same thing for equals quartile A, comma, 3. So this is Q3. Right? So Q1 7.7, Q3 is 12.5. There you go. And if you want to find the IQR, so IQR, QR, you would do this value right here. So let's do equals D5 or D6, D6 minus, or sorry, D5. No, D5 minus D4, D4. So notice what I'm doing there is I'm just identifying the cells here, right? So this is D5 and this is D4. So I'm just putting in the formula of the IQR is Q3 minus Q1. That's all I'm doing there. I don't know if Sheets has an IQR command. It might. Let's find out. Oops. Equals. No, I don't think so. No, it doesn't look like they do. You can look around and find one, but it's easy enough to calculate it yourself. You just calculate Q3 and Q1. It does have range, so you can do min and max, right? So minimum is min of column A. I'll tell you what the smallest value is, and maximum command is max. There you go. Okay, so there's your min and max. And if you want to find the range, you would just subtract these two. So that's how you do this all in Sheets. They just have commands. Median, the command for median is equals median. The command for mean is equals average. Standard deviation, it's equals STDEV. Q1, it's quartile, and then you identify that you want the first quartile. Q3, same thing. And of course, you don't need to do Q2 again, because we actually already did that, right? That's the median. And then IQR, minimum, maximum, all the min and max are commands. IQR, you have to calculate yourself, range too. Okay, let's see how to do all of this in your calculator. I believe I still have that open. Let's go make sure. I do, look at that. Okay, so here's the calculator. Again, I don't know how easy that is to see, so let's pull this up. Okay. So I still have the data that I had in here from before. So there I've got some random data in L1. So if I want to find all of that stuff that I just talked about, it's all found automatically by one variable stats. So I'm going to stat, calc, one variable stats. And I want to do this in L1 because that is where I put all my data. And again, if you wanted to change that to a different list, because you put your data in a different list, like if I wanted to change it to, let's say, L4, I would hit second and then 4. And that would give me L4. But I don't actually want L1, which is the thing we had originally. Frequency list, we're going to ignore for now. We're just going to calculate it up. And if you recall this data from my last video, mean 9.75, and then we found the median of 11.5, and then lo and behold, minimum, maximum, Q1, Q3, right? All there, and then 2 different versions of standard deviation. And the reason it gives you 2 different versions of standard deviation is that your calculator does not know whether you put in an entire population or just a sample. 95% of the time, the one you want is S, the sample standard deviation. Again, if you have the data for it, it's probably a sample and not a population. So almost certainly this is the one that you want, 17.15. Very occasionally, we will actually put an entire population into the calculator and we would want this one, but almost always S is the one that you're looking for. Okay, that's how you find standard deviation. By the way, this is how I'm expecting you to find standard deviation. I'm not expecting that you're going to do it by hand. I don't want you to do it by hand. It's just a giant waste of time. It's a big hassle. Don't do it by hand. Do it in a calculator or computer. Okay. I believe that is the last thing I wanted to say. So let me cut myself off there instead of going off on another rant of some kind. And just say that I will see you guys in the next video.